Okay, this is the Unit 14 practice exam. I'll quickly be going through this here. Multiple choice question number 1. A solution is what kind of mixture? You should know that it is a homogeneous mixture. Homogeneous means it's the same throughout, so solutions need to be the same all the way through. In a solution, the substance that's being dissolved is known as the solute. That's A. So solvent is what's doing the dissolving, is like the bigger thing. Solution is the mixture of the solute and the solvent together. Soluble means something can be dissolved in something else. If you increase the surface area of a substance by crushing it up, the substance will dissolve faster. This is just one of the 3 ways that you can make something dissolve faster: crushing it up, mixing it with like a spoon or something like that, or heating it up. So those are the 3 ways that you make something dissolve faster. If you increase the number of particles dissolved in a solution, the boiling temperature will go up. And so the deal with this one, you have boiling point elevation when you dissolve something in a solute. You have freezing point depression. So the boiling point goes up, the freezing point goes down. Number 5, propanol is a polar liquid at room temperature. It would likely mix with water. Okay, the deal here on this one is that this has to do with the rule like dissolves like. And so polar substances dissolve into other polar substances, nonpolar substances dissolve into nonpolar substances, and they don't mix very well. And so you should know, I've got a list of like 5 different things on the solubility notes that you need to know in terms of whether they're polar or nonpolar so that you can answer these sorts of questions. Number 6, which of the following is an example of a gas solution? You have to know that a gas solution has a solute dissolved into a gas. And so carbon dioxide and water, in that case, that's a liquid solution because it's dissolved in water. Oxygen gas and helium gas are pure substances, so that's not going to be a mixture. So air is what we're looking for here. When a substance is holding more particles dissolved in it than it normally should at that temperature, this is the definition of supersaturation, all right, which is C. For these next questions, we're going to be using this solubility curve. The first one, it says how many grams of NH3 would be dissolved in 100 grams of water at 90 degrees Celsius. Something here, this 100 grams of water, you should just kind of ignore that because all of these are for 100 grams of water. It says it there on the side of the chart. And so the 100 grams of water is just kind of extra information so that you know that it's relevant when looking at this chart. And so we're looking at how many grams of NH3 are able to be dissolved in water at 90 degrees Celsius. So we find 90 degrees Celsius, we go up to the NH3 line, that is this line right here. Okay, and so if we find that point, it looks like something like 11 grams would dissolve in there. So it is C. For number 9, it says 75 grams of NaNO3 is dissolved in 100 grams of water at 30 degrees Celsius. The solution is, so this one we're looking up 75 grams and 30 degrees Celsius. Those are the important parts. So we find 75 grams, 30 degrees Celsius. That's right here approximately. This dot is below the line for NaNO3. If you find the line for NaNO3, it's up here. So since it's below the line, that means it is unsaturated. For question 10, it says 25 grams of KClO3 are dissolved in 100 grams of water at 20 degrees Celsius. So again, the important information here is that we got 25 grams and it's at 20 degrees Celsius. So we find that 25 grams, 20 degrees Celsius, that is right here, approximately. You find the line for KClO3, that is down here actually. Oh, it's this line here. And so this is above the line, which means it is supersaturated, so C. On the back page, we have a bunch of problems here, so they're all mathematical. I said don't worry about sig figs on these, so just go through and calculate them out. So this first one here says you have 50 milliliters of a 2 molar MgCl2 solution. How many grams of MgCl2 do you have? So for this one, the first thing that we're going to take advantage of is this equation: molarity equals the number of moles of solute over the liters of solution. Now, it's important that you remember that this V has to be in liters if you're using this equation. So I gave you the volume in milliliters, so you got to be careful about that. The molarity is 2. This equals the number of moles over 0.050 is our volume, because we got to convert that milliliters to liters. And so then the next thing we have here, number of moles, you can find that by multiplying 0.05 on both sides. Number of moles equals 0.1. Then we've got to get that to grams. So if we've got 0.1 moles of MgCl2, you can look up on the periodic table the molar mass of MgCl2. It's 95.21 grams of MgCl2 in 1 mole. All right, multiplying those by each other, you get 9.521 grams. Looking at the list, looks like we are talking about answer D. For question 12, what volume of solution would be needed to create a 7 molar solution with 10 moles of NaCl? So on this one, again, we're using that same formula: molarity equals number of moles of solute over the volume of the solution in liters. So for this one, molarity is 7, number of moles is 10. We're looking for the volume. Multiply that V to both sides and you get 7V equals 10. Divide by 7, you get V equals, let's see here, 1.43 liters, okay, which is answer B. For 13, it says a solution starts out with a volume of 150 milliliters and a concentration of 15 molar. If you want to dilute it down to 3.0 molar, what should be the new volume? So this is a dilution problem, which means you're using M1V1 equals M2V2. On this one, because volume's on both sides, it actually doesn't matter what units it's in. It's just got to be in the same units in both sides. So if we put milliliters in, we'll get milliliters out. Or if you're comparing two things and one's given in milliliters and the other one's given in liters, you need to get them to be the same units and then multiply it. So, but this one, not too bad. The first molarity there is 15.0 times the original volume, 150. All right, equals, we have the final concentration as 3.0. We need to find the final volume, so we're looking for V2. Just take 15 times 150 divided by 3. You get V2 equals 750 milliliters. So that is A. 14 is talking about freezing temperature of water. So this is a freezing point depression problem. Some things that we need to do. We always need molality in these problems. Molality is the moles of solute over the kilograms of solvent. And so we need to find that. We need to determine the Van 't Hoff factor. It's ZnCl2. That's ionic, which means it's going to split up because it's got a metal and a non-metal here. And so I is going to equal 3 for that one. So keep that in mind. So we got to get this to moles of solute to plug it into the molality equation. So we know it's 45 grams of ZnCl2. If you look it up on the periodic table, you can find that there's 136.31 grams in 1 mole for ZnCl2. Multiply those together, you get 0.330 moles. All right, then to get it to molality, we know that molality equals the number of moles of solute over the kilograms of the solvent, which equals, in this case, 0.330 over 2 kilograms, it said, which is equal to 0.165 molal. All right. Now we're ready to plug it into the equation. So we know that the change in boiling temperature, or change in freezing temperature, equals I times the molality times the freezing point constant for water. In this case, we said that's 3 times the molality, which is 0.165. I think that should be. And then times negative 1.86. That's the KF constant. It's listed at the top of the page, so you don't have to memorize that one. You calculate that, you get negative 0.921. Okay, and so just kind of something to think about here. This means that your freezing temperature equals negative 0.921 degrees Celsius. Freezing temperature and change in freezing temperature aren't the same thing necessarily, but because with water the freezing temperature is 0, it ends up looking like it's the same thing, because if you change negative 0.921 away from 0, you get negative 0.921. But if it was boiling, for water the normal one is 100, and so you're going with a change from 100 for that. Or I might tell you the normal boiling point of a different substance, and you'd have to work with that, or the normal freezing point of a different substance, and you'd have to work with that. And so if we look at these answers, this is actually not listed on any of those, so this is E, none of these. Watch out for that because I have the positive version of that number on there, so you need to know that it's negative. Don't get tricked by that. All right. Question 15, you dissolve 4.0 moles of heptane, which is the C7H16, into 8 kilograms of an unknown solvent. The boiling point for the solvent goes up by 0.55 degrees Celsius. What is the boiling point elevation constant Kb? So something here to notice, this is a hydrocarbon. It's just nonmetals, carbon and hydrogen. That means it's not going to dissociate, so I equals 1. It doesn't spread out when you put it into a solvent because it doesn't, it's not ionic, so it won't spread out. So putting this in here then, we know that change in boiling temperature equals I times the molality times the Kb. We are trying to determine the Kb in this case. The change in boiling temperature was 0.55 degrees Celsius. I said Van 't Hoff factor is 1. The molality, we have to calculate that. So molality equals 4 in this case, the number of moles of your solute over the kilograms of solvent, which equals 0.5 molal. All right, then we'll plug that in, so 0.5 here, and then times Kb. Solve that for Kb, basically just dividing both sides by 0.5, and you get that Kb equals 1.1 degrees Celsius per molal, which is A. All right, as always, if you have any questions on that, make sure that you come in and ask.